Hello everyone, I'm Yao Liu, and I'm from MPI for Informatics. Today I'm very happy to have the opportunity to present our work, an ensemble of Epoch-wise empirical base for few-shot learning. This is the joint work with Brent Schiller and Qianru Sun. Most deep learning algorithms are based on supervised learning. So we need lots of labeled samples to train the model. However, for some tasks, we don't have enough labeled data. For example, it is hard and expensive to get labeled medical images. Sometimes, we need to hire a medical expert to label the dataset for the task like mitosis detection. So the question arises, how to learn a model with limited labeled data? We formulated the task as few-shot image classification. We use many shot syn-class samples and few-shot unsyn-class samples to train a classifier. And the trained classifier will be evaluated on the test samples for the unsyn classes. To tackle this problem, people generally reorganize the syn-class samples to many few-shot tasks. We use this task as the training task, then we meta-train a model on this task. And then we adapt it to the unsyn class task. We call this process meta-learning. Existing methods like MIMO, MTL, and SIB, these methods use a single base learner and arbitrary base learning hyperparameters, so the training process is unstable. For our method, we use an ensemble of multiple base learners and task-specific base learning hyperparameters, so the training process is stable and more robust. In the following slides, I'm going to introduce the details of our method. First, let me briefly introduce one famous related work, MIMO. The idea of MIMO is to learn initialization weights theta by meta-learning. In MIMO, when we get a new training task, we use theta to initialize the first base learner, theta 0. And then we update theta 0 by gradient descent and get the second base learner, theta 1. We repeat the process for m epochs and get theta m. We use the final base learner theta m for the prediction. And then we calculate the meta loss for this task from the prediction. And finally, we use meta loss to update the initialization weight theta by meta gradient descent. We repeat all these steps for different training tasks. We can see that for each task, we actually calculate m different base learners, theta 1 to theta m. However, we only use theta m for the final prediction. That means we don't make use of the theta 1 to theta m minus 1. In few-shot learning, we need to make most of the information we have and should not discard these base learners easily. And also, we use an arbitrary base learning rate for all different base epochs, even for different tasks. It is obvious that the optimal base learning rates for different base epochs and different tasks are different. In our method, we calculate the predictions for each base learner. That means we have m different predictions, z1 to zm. We design a model called hyperprior learner. During base learning, we input the training data and the gradients from different base epochs to the hyperprior learner. Then we output the combination weights V1 to Vm for different base learners from the hyperprior learner. The final prediction is the weighted sum of the predictions from different base learners. We also generate task-specific learning rates alpha1 to alpha m for different base epochs from the hyperprior learner. And finally, the hyperprior learner is also updated by the meta-gradient descent. In this way, we make use of the base learners we already have and achieve a more stable training process and more robust predictions. We also generate different hyperparameters for different base epochs and different tasks. In terms of the architecture for the hyperprior learners, we have two options. For the epoch-independent setting, we use fully connected networks as the mapping function. For the epoch-dependent setting, we use LSTM networks as the mapping function. The hidden states are from previous base epochs. The experimental results show that our method can boost the performance on different baselines with only a little additional computation and a few additional learnable parameters. For example, plugging in our method to Memo achieves 2.9% of improvement on average. And it adds only 2.2% learning parameters to the original Memo model. And it gains only 9.7% average overhead regarding the computational time. Figure A shows the values for the generated learning rates alpha. The base learners working at later training epochs tends to get smaller values of alpha. This is actually similar to the common manual schedule. Figure B shows the values for the combination weights V. We can see that base learner 25 instead of base learner 100 gain the highest V values. Our explanation is that during base learning, base learners at later epoch get more overfitted to the field training samples, so their functionality is thus disabled. For more details, you can visit our project website. The open source code is available on GitLab. Thanks for listening and feel free to email me for any questions.